Hello. Yes, Raina. Sorry. I was muted. Can you hear me now?
Yes, sir. Yes.
Okay. Now the question 3 is saying that they are asking the fast charging current for a given schematic. Okay. And the IC is given that BQ24040. Some particular resistance will be given, that is the R set 2, R preterm, and RTS. Okay, these resistance are given. The battery capacity is 700 mAh and the rated voltage is 3.8 and maximum voltage is 4.2. So how we solve this question is that they are asking, first question is the fast charging current. So if you see here, hmm, yes, if you see here in that particularly data sheet, there is one particularly fast charging current factor is given, K set. Okay, and that particularly fast charging current is for 24040. Okay, basically we are talking about 24040. Okay. uh, okay, so this fast charging current factor is given K I set. So we required a K I set because the formula for R I set is equal to K I set upon I out. Okay, we have to calculate the I out. So I out is K I set upon R I set. Okay, K I set is, now you can check here. One more thing is the battery capacity is 700 mAh. Okay, so if we calculate, we are using this formula. What is the value of K I set? According to this one. Okay, according to this one. So we have a value of 540. If you have any doubt, you can change the value also, calculate what is the I out. So if I put the value all three, so that is a 520 divided by 740, 527 divided by 740, and 540 divided by 740. We have a three values. Okay, these three values, according to these three values, I calculate the I out. And every time the value of I out is greater than 50 milliampere. So that means which one is the correct one? According to the 50 milliampere, this value is correct, 540. So we neglect these two and only calculate this, particularly 540 divided by 740. So if you calculate it, mm, 540 divided by 740. So it is 729.7 milliampere. Okay. Now any doubt? Now the fast charging current is this one. Our battery capacity is 700 mAh. Okay, so how much time it will be take to charge? 729 by 7 milliampere. So milliampere and milliampere is cancel out. So that value is 700 divided by 729 hours. So 700 divided by 729. So it is a 0.96 hour. Now if I want to convert into the minute, I multiply it with 60. So I am getting a 57.6 minute. Okay. Now it is saying the current come down from the charger to signal that charging complete is milliampere. So first of all, for this one we have to calculate. We already calculate the fast charging current. Now we have to calculate the current come down factor. So current come down is basically dependent on percentage item. Okay, that is on percentage item. Now for the percentage item, if you see the formula, yeah, here R pre-term is equal to K pre-term multiplied by the percentage of term. Okay, so we are using this formula. So according to this formula, our percentage term is right term is equal to R pre-term divided by K term. Now what is K term? If my pre-term resistance between 2 to 10K, okay, between 2 to 10K and fast charging is 10 to 50%. So we are using this particularly value. If my value is from 1 to 2K, that means lower than 2K, we are using this value, and 2 and more than 2K, we are using this value. So what is K pre-term? 200. What is R pre-term? That is in question. If you see the diagram, R preterm resistance connected with preterm terminal is 2000 or 2K. So 2000. So that is 10%. Okay. So that means before termination, 10%. That means if we are saying the 100% is a battery, so till 90% the fast charging will be done. After that, the termination will be start. Okay, in the last class, if you see, if you remember, I just explained the charging will be done in three different phase, not exactly zero. The basically is current will be start like that. You remember last class where I draw this particularly, this region is called the fast charging. Okay, this one is called the termination. Okay, here it will be the voltage, here it will be the current. So in the termination region, current is increasing very less, whereas the voltage will be increased. Okay, in the fast charging current, the voltage is increased very less, where the current increased rapidly. And before that one, it is a setup reason. In this, voltage and current both will be increased in a same manner. Okay, that means current is also increased, voltage is also increased. So we already discussed that one. Now he in the question it is asking that when we reach at this point, okay, So from here to this point, how much is required? Okay, we see that total current is out current is how much? 729. Okay, 10% of the termination current, that one. So that means how much is the uh, current come down? 729 into 10% of that one. So that means 72.9 milliampere. So that means in this region only 72.9% 9 milliampere current will be increased. Okay, so that is question number third, fourth, fifth. Clear? Yes. Okay. Now we move to the week 10. In the week 10, question number 4. Week 10, question number 4. Yeah. In the given figure, the maximum load current delivered to external circuit is 100 milliampere. The load regulation is millivolt when the voltage is 4.2. Now, how we solve this question? What is load regulation? Yes. Now, initially, the load regulation is basically respective to the change in current. So, initially, we are saying that load current is 0. So, this is my V in, 10K, 10K, V out. Okay, let's assume that I load is 0. Okay, I load is 0. So, if I load is equal to 0, so the V out is V in into the drop across this voltage, so 10K divided by 10 plus 10K. So that is V in divided by 2. Now V in is 4.2, so 4.2 divided by 2 is 2.1 volt. Second case, the external current is 0. So basically there is one current, external current is 100 milliampere. Okay, so if we are saying that the external current is 100 milliampere and that particularly connected with the 10K ohm resistance, so can I convert this current source into the voltage source? So this one is the V in with resistor 10K, with resistor 10K and one voltage source. Okay, current is going downward, so that means the direction of current will be negative connected with 10K and positive connected with ground. Now, what is the voltage of this voltage drop voltage source? That is I multiply by the R. Okay, you already discussed that how we convert a current source into the voltage source. So I am just using that current source connected in with resistance in parallel is equivalent to voltage source connected in series. So I am using just only the source transfer. Okay. Now the voltage of this one is 100 multiplied by 10. Sorry, this is 10 ohm, not 10k. This is 10 ohm. 100 multiplied by 10 into 10 raised to the power minus 3 because of milliampere. So that is 1 volt. Okay. Now what is V out? So first of all, we calculate the current I. I is V in plus 1 volt. Why? Because positive connected with negative. So basically these two battery voltage will be added, divided by 20. Okay, so 4.2 plus 1, 5.2 divided by 20 ohm. So 0.26 ampere is the current. If 0.26 ampere is the current, so that means the voltage drop across this one is 2.6, and the voltage drop across this voltage source is also 2.6 volt. Okay, the direction of this one is this become plus, this become minus. Now the V out is, yes, what is V out? Negative connected with negative, positive connected with this positive connected with V out, and this positive connected with ground. So basically the voltage is connected in series but with opposite polarity. So there is a voltage difference. So 2.6 minus 1.0, that is 1.6 volt. Now how much change in the voltage? dV out. I just say this is the V out 1, V out 2. So V out 1 minus V out of 2. So that is 2.1 minus 1.6 is equal to 0.5 volt or 500 millivolt. Okay, that is question number 4th of graded assignment 10. Clear?
Sir, I
Yeah.
have one doubt.
Yes.
Sir, how do we know if a current source is going to ground or towards V out?
Because it is saying in the statement, na? The statement, read the statement carefully. If maximum load current delivered to external circuit is 100 milliampere.
Okay.
That means current is going outside because otherwise we can't deliver. If we say that
Okay,
the
okay.
maximum current load that is added to from the external circuit, then we change the symbol of that current
So then
source.
polarity will also change, no, sir?
Yeah, polarity is also changed as well as the basically the voltage load regulation. If we say that we are taking in this way, I'm just using this is the resistance 10 ohm, 10 ohm, and this one. Okay, now calculate. Again we are taking the 100 milliamp, so basically it will be equivalent to V in 10 ohm connected with 10 ohm, and the direction of this one is this 1 volt 10 ohm. Now the current is I is V in minus 1 volt. Why? Because V in is positive and positive connected with positive, so voltage will be subtracted. Okay, divided by 20 ohm. So that is 4.2 minus 1, 3.2 divided by 20 ohm. So that is 0.16. Okay, so here the drop is 1.6, here the drop is 1.6. Throw this one. The direction is plus minus. Now what is V out? Both voltage will be added 1.6 and 1 volt because positive now connected with the negative. So V out is 2.6 volt. Okay. So what is the difference del V out? 2.6 minus 2.1, again that is 500 millivolt. But we change the direction. Calculation is changed, direction is changed.
Okay, got
Okay.
it, sir. Okay, sir. Thank you.
Okay, that is question number 5. Question number 4. Basically, there is some issue in the question number 4, but I will tell you. Question number 4, we have to calculate the variance of the output voltage. So sigma square del V out upon V out. That is, if you remember the formula, R1 upon R1 plus R2 square divided by del square del R1 upon R1 plus sigma square del R2 upon R2. Okay. So R1 and R2 is not given. So because of that one, we can't calculate this one. But if I say R1 is equal to R2, so that is 1 divided by 2 square. Now del R1 by R1, we know that what is the del R1 by R1? It is 0.33%. Okay. So we are taking 1 by 3. Because we calculate all the values in the percentage also. Okay, variance is also calculated in percentage, so I am not removing this percentage. So that 0.33 is 1 by 3%. Okay, so the variance is 1 by 3% square plus del R1 by R1, so the variance is 1 by 2 because it is 0.5%. So 1 by 4, 1 by 9 plus 1 by 4. If I solve this, so 1 by 4, 36, 13. So that is 13 divided by 4 into 36. So 13 divided by 4 divided by 36. So that is 0.090%. Okay. Because output voltage is dependent on only on the resistance. So we are, if we calculate the variance of the output voltage, we check the what is the resistance distribution is there. Okay, resistance distribution is there. So only we calculate the variance of the output voltage in terms of resistance. Clear? Hmm. Okay, now the next question is week 11, 1, 4, 6, and 8. Week 11. If the noise voltage in the input supply is 30 milliwatt at 10 kilohertz frequency, the noise voltage at the output V out. With the noise voltage, so we have to check the low dropout voltage regulation IC. Yeah, what is the effect of this noise voltage? So basically you are asking that what is the role of the frequency. Every component has a role of frequency. I think if you are aware, what is the diode characteristics? This one, I think you know that what is this is the diode characteristics. Any issue, any doubts? Or we can say that, like for example, if we say that this is my resistor, R, we apply the voltage, the current is flowing. So what is my voltage versus current? So V and I. Okay, because we know that V is equal to IR. So basically the relation between V and I is 1 by R. Clear? Any doubt in this particularly equation, in this diagram? Now if I change the frequency, what will be happen? Is this particularly characteristic is same for all the frequencies? No. For the lower frequencies, this characteristic is okay. You are using the carbon resistance, so for a lower frequency the characteristics is okay. But if we go switch into the higher frequencies, these resistance characteristics is also change. They will show like this type of graph, the VI, like this type of graph they are showing. If we increase the frequency 50 megahertz, 100 megahertz, so for this we have to use resistance that will operate for the high frequencies. Okay, that will operate for high frequencies. So because of the frequency the vibration is done. Okay, structures, in every structures either we are taking the semiconductor, conductor, insulator, so every particularly structures have the electrons pair, electron and holes pairs, or maybe the free electron that will be responsible for conduction of current. Okay, now if we increase the frequency, because of that frequencies the vibration is done. Okay, and because of that particularly vibration the response of that device will be changed for higher frequencies. Okay, so if you are using the resistance, normal resistance for a high frequency, the particularly response is different. Similarly thing is that if we go with the question part, here you can see that you are using a low dropout voltage regulator, TLV743P. So that particular device also having a different response, different gain. All the parameters should be different for the different frequencies. Okay, so that is the role of frequencies. Clear?
Yes, sir.
Raina? Okay. Diode characteristics is also not same. I don't know you are aware with the diode characteristics or not, but it will be changed when we increase the frequency. More than 50 or 100 kilohertz, the response is different. Okay, more than 100 megahertz, the response is completely different. Okay, so for that particular reason, we are moving to the high frequency components. Now we move to the MOC. So in the MOC part, everyone solve the MOC test, or should we wait till tomorrow? Everyone try to solve that MOC, or should we wait till tomorrow?
So we can do it tomorrow.
We can do it tomorrow. Okay. So till that, I think you will do that. I just give you a little bit hint about that. Okay. We have a two capacitors in question number two. Okay. For every capacitor is a non-ideal capacitor. So first, I think you solve. Second, if we go with the capacitor, so they have a two capacitors. Every capacitors have a equivalent is they have a inductor, they have a capacitor, they have a resistance. Okay, so what is the frequency? F is equal to 1 upon 2 pi root of LC. Okay, now if we are saying that if this particularly capacitor will work on that particularly frequency, what is the impedance of that frequency? Is R, because in you know that the resonant frequency will be occurred when omega L is equal to 1 upon omega C. That means impedance of inductor is equal to impedance of capacitor. Okay, and both are having the 90-degree phase shift, so they will cancel out to each other. Okay, so this will be and this will be cancel out to each other. So particularly at that frequency, the value of impedance is resistance, normally resistance. This is the question number two. Okay, question number three. This resistance P dot connected here minus plus. This is the VI R1 R2 R4 R3. Okay, so we assume that this voltage is VA. This voltage is VB. So can we apply the KCL? So the current that is coming, it will be distributed in two part, one part and this second part. Okay, one part is this one and second part is this one. Yeah. Now you can say that this particularly current is zero, but no, this is not zero. By why? Because this is a non-ideal op amp. So the output voltage V out is nothing but A time V positive minus of V negative. V positive is 0, so I can say minus of A V negative. So we calculate this negative voltage, that is VB in this diagram. So A time VB, that is V naught. Okay, A is given that it is 1000 by S. Now we have to calculate the VB. So for VB, we can say that the current will be going in two parts. So I1, I2, I3. Okay. No, I understand. So I1 is equal to I3. This is my first equation. And second equation is that I3 will be again go into I4 and I5. I5, I4. So I3 is equal to I4 plus I5. That is my second equation. So use these two equation. Calculate the value of I1, I3 from this figure. Put all the values of I1, I3, I4, I5 in this equation. Solve that one for VB. Okay, solve that one for VB. Now put the value of VB and put the value of A. You can calculate the V naught. Now in this R4 is unknown. Okay, R4 is unknown. So we have to equate this particularly V naught upon Vi is equal to 4 upon 1 plus 0.007 S. So equate using this. If we calculate, so equate that one is here. Okay, equate with this one. So you can calculate the value of R4. Hmm. Question number 4. If I change my V in voltage from 3 to 4, what is the variation in the output voltage? So here you can see that this is a negative connected with 10K. Here it is connected with 10K. V out RL. Here we apply V in 20 and 30K. That is positive. Okay, so first of all, we calculate the gain. A is nothing but it is a non-inverting amplifier. Why? The supply will be connected on the positive terminal. So it is a non-inverting amplifier. The gain is 1 plus RF by R1. Okay, RF is 10, R1 is 10. So 10 by 10 cancel out, so gain is 2. Now what is V out? V out is A time V in. That means this one. And what is V in? V in will be the apply with the voltage divider by 6. So V in, I just say the V in 1. So V in 1 is nothing but V in multiplied by 30K divided by 50K. So you can calculate the V in 1 from here, put the value of V in 1 here. So you can calculate the 2 voltage V out when V in is equal to 3 volt and V out when V in is equal to 4 volt. Okay. Now the first question is you have to calculate the delta V out. This is your first question. Second question is resistance R1 has a maximum variation 4% and while resistance R2 has a maximum variation of 4%. What is the maximum variation in the V out for a given V in? Okay, now you can see that when V in is changed, V out is changed. So basically, if I calculate the variation in V in voltage, can I calculate the V out variation? Okay, why? Sorry, Vx. I just say that it is a Vx. If I calculate the Vx variation, Vx variation, can I calculate the V out? Why? Because the relation between V out and Vx is V out is 2 times Vx. Now Vx variation is dependent on which two resistance? R1 and R2. Because Vx is dependent on this resistance and this resistance. If I change the value of R1 and R2, the Vx will be changed. Okay? And the variation in this R1 and R2 will be given. Variation in these two resistance will be given. So you can calculate the V in variation first, and then with respect to V in, you can calculate the V out variation. That is the second part. Now third part is that if the open loop op amp has a DC gain of 10 to the power 6 and open loop resistance is 1000. Calculate the change in output voltage when the load current goes from I to I load. Okay, now we have given a open loop resistance also 1000, and I load will be changed from 0 to 40 milliampere. So first we assume that there is no current will be going. Like I'm just saying that this is a completely black box. We have initially we say that IL is 0. Next we say that what is the IL is I load max, and that is 40 milliampere. Okay. Now in both scenarios you have to calculate what is the variations in the output voltage. The similar question that we do solve. The similar question that we solve. In this black box, I just assume that there is one voltage divider biasing and it will be connected with here. Okay, when IL is 0, so that means the device will be like that. Okay, this is the grounded V in. When IL is 40 milliampere, so this is the V in. We have a 40 milliampere. Okay, the similar question we solved in the week 5. So just try these 4 questions first. In tomorrow class, we will discuss that. I give you the hint. On the basis of that one, you will try to solve it. And if you have any difficulty, we will discuss that.
So can you just try for first question also, like which are the equation?
Okay. So we have to given that V out by V in. Hmm. So we have minus plus connected with 1K. Resistance 10 picofarad. Yes. So in this particularly question, if we say that we have a two different equations we are created. One equation, if we solve that, we can say it is The first point, this positive will be grounded, this positive will be grounded, there is one resistance. This is V in. So we assume this is the VA point, this is the VB point, VC point, and VD point. Okay, so basically there are two particularly devices. One is this one, and second one is this one with this resistance and this capacitor. Okay, so there are two particularly. Which type of filter is this? Yes, which type of filter is this? R connected in series and C connected with parallel.
Low pass, sir.
Low pass. If you check, this is the VA, so V in minus VA by R is equal to VA minus V out by 1 by CS. VA is 0, so this is 0, this one is 0. So V in divided by RCS is equal to minus V out, and V out by V in is equal to 1 upon RCS. Yeah, that's fine. Now we have a two particularly low pass filter. One filter is this one filter is this one, and both will be connected with this resistor. Okay, so we are saying the V out by V in is equal to, if we are taking only these two circuit first, so 1 upon 1 plus RCS square. Or you can do one more thing here, is that you directly calculate the transfer function of this one V in using this capacitor and this resistor outside. You can calculate this particular transfer function of this one. This one. Okay, we are not including the second one. We are directly calculate the transfer function of this one. So what is that? V in minus VA. We say that the current that is coming from here, it will be go into two parts. One is this one, second is this one. So V in minus VA upon 1K is equal to VA minus VB upon 1 by CS plus VA minus V out upon R. Okay. VA we know that 0. Why? Because of the virtual ground concept. The positive terminal voltage is 0, so that means the VA is also 0. So VA will be eliminated 1, 2, 3. Only the equation is in terms of V in, VB and V out. Now we have to eliminate the VB. So how we do the elimination of VB? From that second circuit. I am considering the second circuit. This one. This is my second circuit. Okay. So what is the equation for second circuit is the current that is coming from VA. So VA minus VB by 1 by CS is equal to the current will be going in this one. So VB minus Vx upon R. Sorry, VB minus VC upon R. Not on this one, we apply here. VB minus V out from this point VB to this V out. VB minus V out upon R plus 1 by CS. Now VA is 0, so that term is 0. Can I calculate from this equation is VB is equal to in terms of V out time X from the equation second. Now put this value VB in this equation first. Okay, so now VB is eliminated because VB will be in terms of V out now. Okay, VB is eliminated. Only the terms equation will be in the terms of V in and V out. V in and V out. Clear? Now you can solve this particular equation and calculate V out by V in. Okay, any doubt? Yes, any doubt?
No, sir.
Okay. So just try it once. We will solve that one in tomorrow class. If you have any other doubt, you can ask. For the end term, there are 4 questions. I already tell that one question is from week 1 to week 3. Second is week 4 to week 7. Week 1 to week 4 and week 5 to week 7. And 2 questions from week 9, 10, 11. If anytime you are basically any doubt, just G space, we are connected on G space, just put your queries in that. No issue. Okay, any particularly doubt related to any concept, you can put your queries on G space anytime. Yeah. Thank you and Prepare well. All the best. See you tomorrow.
Thank you, sir. Thank you.